Okay, so let's look at the time-dependent perturbation theory. So we start with some initial state at the time, let's say minus t, at some earlier time. Our initial state will be, for example, two particles moving towards each other. And of course, this state will evolve in time. We know what it is at some t0 is equal to minus t. And we will look at it, what happens to this particle at some later time. Let's say that at t is equal to capital T. So at t is equal to minus t, we have these two incoming particles. Something happens, they collide. And at the far future, let's say we will be looking at this state. And the question I will ask is, what is the probability that this is at some given state f? Now, I know what this is, what this state is. The evolution is given by the Hamiltonian. So it will be f e to power minus I h times 2t times the initial state. In the initial state, whenever I'm talking about initial states, just remember that it is at the time t is equal to minus t. And eventually, I will take the limit as capital T goes to infinity. So at a very early time, I create these particles, I send them to each other, they interact somehow, and then I see what will come out of that interaction at a much later time.
Sorry, what is written right at the first inner product? Is that an E t0 equals minus t?
That is my state is I, that's my initial state, that I create at, well, let me remove the zero if you want. At t is equal to minus t.
Time terms are under parentheses, right? Or something.
I just know how to read that. I mean, beyond that, it's not really important. At t is equal to minus t, my state is in the ith state. Then it evolves in time. At a later time, t is equal to capital T. I would like to find what my final state is. What is the amplitude that it will be in some given final state f.
Why we choose the initial time minus t? Normally it chooses 0, right? It's chosen 0, right?
Well, I mean, because it's easier to choose at minus t. I will assume that they interact at the time t equal to 0. That will be my assumption, my definition of the times. I create them somehow, let them evolve for a very long amount of time, and then they interact. And then wait a very long amount of time further after that they interact, and that is when I'm making the measurement. So I'm defining my t is equal to 0 as the interaction time when my particles are interacting. At a much earlier time, that is t is equal to minus t, I create them. At t is equal to, at a much later time, at t is equal to capital T, I measure them. And this is what I would like to calculate. This is in fact defined as SFI, the S matrix. Of course, I also need to make sense of that limit. What do I mean by t goes to infinity? Because you see there is the, okay, it's the exponent of an oscillator with an infinite coefficient. Those are the things that we still need to address. Now, let me remind you the pictures, the various pictures we had in quantum mechanics. There is the Schrödinger picture. where the states depend on time. And then you have operators that are independent. For example, the position operator doesn't depend on time in this Schrödinger picture. The expectation value of the position operator does depend on time, but not the operator itself. The expectation value depends on time because, at least in this picture, the state is changing with time. So the position of the particle will also change, the average position of the particle will also change in time. Now, those expectation values are defined in this way. These are the expectation values of the operators. I know how my states evolve in time. So if I know the wave function at some reference time t0, this is how things will evolve with time t. This is the expectation value. Well, then I can say that, let's say that this is psi t0, which is independent of time t. This is my Heisenberg picture state. This is independent of time. But now the operators. These depend on time. Well, at the end of the day, I'm always calculating some expectation values of some kind of an operator. And whether you are using the Schrödinger picture or the Heisenberg picture, the expectation values are all given by the same expression. The only difference is how you group these time evolution operators. Do you group them with the states, that gives you the Schrödinger picture, or do you group them with the operators, that gives you the Heisenberg picture? And typically you choose t0 as 0. And at t is equal to t0, the state, the Schrödinger picture state, and the Heisenberg picture state, they are the same. And the Schrödinger picture operator is equal to the Heisenberg picture operator at t0. So at t is equal to t0, whatever you choose at your t0, these two pictures overlap, but the time evolution in one of them, time evolution of the expectation values is in one of them attributed to the operators, in the other one it is attributed to the states. Now let's come back to the problem that we are having at the moment. We have a Hamiltonian, which we say that we can separate into two parts. This separation is kind of arbitrary. The only criteria I have for this separation is H0 is exactly solvable. So there is a part that I can solve exactly. And V, hopefully, small in some sense. So there's when you consider the evolution of states or operators, well, they will evolve, their evolution will receive contributions from both H0 and V in general. Well, I don't know the solution of this whole system. So whenever you have a system that you cannot solve exactly, what you try to do is you try to solve the part that you can actually solve, and hope that that is the dominant contribution. You try to separate them. Separate the part that you can actually understand and the part that you cannot really exactly solve, you try to approximate it. So that is what we will do also in the time evolution. So whether you are if we use the Schrödinger picture, my states will evolve due to H0 and V at the same time. If I use the Heisenberg picture, my operators will evolve due to both of H0 and V. So I separate these two evolutions. Yes, so this is what I'm trying to calculate. But I know that I can exactly solve H0. So I will assume that my operators will evolve with H0 So these products are just one, identity operators. So I didn't really change anything. The only thing I will change is how I group these time-dependent pieces. So this will be one group. These two will be other groups, which I will combine with the state. In a sense, this is a new picture, so-called the interaction picture. The operators in the interaction picture do depend on time, but that is only due to the part that I can actually solve. Since I can solve H0, I can determine this time dependence of any operator. The other part, the interaction picture state, also evolves in time. It's not just the operators. Both the operators and the states, they are both evolving in time. And this is the time dependence. You see, if V were 0, if there's no potential, then H and H0, they will be equal. So interaction picture will basically be the Heisenberg picture. Now, this I can also write as e to power...
H turns to be a V of small perturbation, right?
No, H is H0 plus V. H contains both of them.
Yeah, that's why, when we, multiply them, then HI V 2 minus T0, I guess, right?
You see, this product...
Yeah.
They are not equal.
Y plus H equals H0 plus Y plus V.
They are matrices. They are operators which need not commute. So they are not equal. But we will have a similar expression. We will derive it. Don't worry. Now, if you go back, this is my interaction picture state. This is the definition in terms of the initial state of my initial state. Now, I can also write it in this form. Remember, this is nothing but the Schrödinger picture evolution. So that is psi of t in the Schrödinger picture. If you like, you see, this is the Schrödinger picture state. Well, Schrödinger picture state evolves both due to H0 and V. I'm just undoing the evolution due to H0. So note the sign over here. It's plus, it's not minus sign. In a sense, it has the wrong time evolution. Now let me define some operator. So this is the time evolution operator in the interaction picture. At the time t is equal to t0, all pictures overlap. Interaction picture, Heisenberg picture, Schrödinger picture. So this state is the state in the Schrödinger picture, the same state in the Heisenberg picture, the same state in the interaction picture at the time t equal to t0. The successive, the later evolution is different in both, in different pictures. So if I go back to this expectation value now, that expectation value can be written as psi t in the interaction picture, my operator in the interaction picture at the time t times psi of t in the interaction picture. You see, since I know I can exactly solve h0, I exactly know what my operator is in the interaction picture. That's the starting point. The only thing I don't know here is that I need to solve is what are these states in the interaction picture. And to determine those states in the interaction picture, I need to determine what this U operator is. So let me see what how does this operator evolves in time. du by dt. Well, the derivative of the first term, which will be e to power I h0 t minus t0 h, e to power minus I h, no, this is h0, t minus t0, plus the first term times the derivative of the second term, which is minus I h the I.
I am sorry, I missed what that part U is.
U is this one. It is the time evolution. It gives me the time evolution in the interaction picture. Also keep in mind that in general, the derivative of the exponent of an operator, this is not equal to this also doesn't hold. In general, it doesn't hold. The reason why it doesn't hold is it's not equal to that if the derivative of the operator doesn't commute with the operator itself. If this condition, if the commutator is non-zero, then the derivative of the exponent of an operator is not just the exponent times the derivative of the exponent. If they commute, then it holds. That is what I'm using over here. h0 commutes with e to power I h0 t minus t0, because h0 is time independent. It doesn't have any explicit time dependence. So I can just put it at the back, at the front, or somewhere in between even. And similarly, h, I can put this h in front of this exponent on the right of that exponent. It doesn't matter because h commutes with the exponent.
So don't linear functions of an operator always commute?
Sorry?
Don't linear functions of an operator always commute with an operator?
No.
The derivative is a linear function. When does it fail to commute?
In general, it does not. Now, here we have a very simple exponent that depends on time. It has a very simple time dependence. And hence, the derivative of the exponent commutes with the exponent itself. You see, physically, the thing that we actually care about is this expectation value. And all these pictures, they give me the same thing.
I couldn't get the difference between Heisenberg, Schrödinger, and interaction picture.
Well, whichever one you like. You see, in the Schrödinger picture, it's the wave function that changes in time. Now, if you keep thinking that, okay, I have this wave function, this wave packet, it moves around, conceptually it might be easier for you. So there you have this wave function that is moving around, which corresponds to your particles. But there, for example, it's not easy to see the Newton's equations of motion. How do they arise from that wave? Heisenberg picture is better in that sense because the Heisenberg picture operators are actually the solutions of Newton's equations in most cases. So if you have a harmonic oscillator system, if you solve for x and p operators themselves will do this harmonic motion. So in that sense, it is more intuitive. This interaction picture is just a trick, somewhere in between those two pictures, that allows us to separate the effect of the potential. And so we can treat it separately.
Hocam, I was thinking of the counterexample of this. I guess we can just say position operator for a Dirac particle, its derivative velocity is not the velocity as the derivative of it. So it won't hold for the Dirac particle, right? This derivative of exponential thing won't hold for the... it can be a counterexample for linear?
Let me give you this example. Sigmas are your Pauli matrices. Alpha j's are some arbitrary functions. Just choose some alpha j. Unless you are very unlucky, you will see that the derivative of that exponent doesn't commute with the exponent. Well, let's go back to this derivative. Okay, h0 commutes with the first exponent, h commutes with the second exponent, so I can use that freedom to put both h0 and h in the middle of those two exponents. Why? Because if I put them in the middle of both exponents, I can just factor out the first and the last exponent.
Hocam, I don't understand. Did you say that this AX with Pauli matrices, they are commute or they do not commute?
They should not commute. Well, not AX, this is. Okay, for example, take this one, they shouldn't commute. Because the alpha j, sigma j, and its derivative, they will be basically pointing in different directions. And sigma matrices pointing in different directions will not commute with each other. Now, back to the derivative of u. Now I can cancel the h0 in h. So this is nothing but minus iv. So du by dt is e to power I h0 t minus t0. Let me put the I over there. Times v times e to power minus I h t minus t0. Still, it doesn't look so nice because I'm taking the derivative of u. I would rather express the result also as in terms of u, so that hopefully solving the differential equation will be easier than calculating that matrix product of two exponentials of operators. Well, I can do my trick. Well, this is nothing but my v operator in the interaction picture. And this is nothing but my u. So I times the derivative of u with respect to t is vi, the potential in the interaction picture, times u. So in particular, you see that if v is 0, derivative of u with respect to time is 0. And so u is just constant, 1, from the boundary condition. So any deviation of u from 1 will be due to this potential V. And hopefully, if V is small, the deviation of u from 1 will also be small. So if you calculate that with deviation from 1, yeah, that will be a small correction, and we can just proceed. Of course, then we need to solve this equation. Well, let's solve it. Let me integrate both sides. From t0 up to some t. Not to confuse the different t's, I just renamed the dummy integration variable to t prime. Well, the left-hand side will be I u t minus t0. Sorry. I u t0 evaluated from t0 up to t. Let me move this minus sign to the other side. Minus I from t0 up to t. Vi of t prime dt prime u of t prime t0. This is u of t0 minus u of t0 is minus I t0 up to t dt prime Vi of t prime u of t prime t0. My boundary condition is, this is 1. Yes, if you look at the definition of u, this is the definition of u. If you put t0 instead of t, both of those exponents become 1. That is my boundary condition. So this is my solution for u. U t0 is equal to 1 minus I, the integral from t0 to t, dt prime, Vi of t prime.
When we're writing the u, we should write u dagger right there.
No.
Boundary condition. But they do not come, right?
They don't commute, but both of those exponents are 1.
How one? I mean, when we...
When t is equal to t0, it's the exponent of 0,
okay.
which is 1.
Okay, sorry.
Well, this is a solution, but not really a solution. I still have u on the right-hand side. Well, I can iterate. Well, let me just rename. I'm just changing the name to T1 now. Well, what is u? Well, u is all of this expression. Instead of u, I can use that whole expression. Well, 1, this 1 will just give me this integral. Then I have plus minus I squared from t0 to t dt1 Vi of t1 Vi of
Can you solve it like Volterra equation?
hold on, t1 Vi of t2
By integral equations, Volterra equation.
Well, I mean, if you can come up with a general solution, great. But these are operators, don't forget that.
That's true. But just functions.
Well, I can iterate it even further. So this will be 1 plus minus I from t0 to t dt1 Vi of t1 plus minus I squared from t0 to t dt1 from t0 to t1 dt2 Vi of t1 Vi of t2 plus minus I cubed dt1 dt2 dt3, t0 to t, t0 to t1, t0 to t2, vi of t1, up to infinite. I have this infinitely many terms. Again, as I said, if v is small in some sense, then one or two terms in this expansion would have been enough. But in general, we have to calculate all of them. Well, I mean, let's do a bit more tricks. You see, we have the differential equation satisfied by u. If these were not operators, but just ordinary functions, the solution were kind of trivial, just the exponent. So it's just u is e to power minus I dt prime v I of t prime from some t0 up to t prime. This would have been the solution if they were ordinary functions. Well, but this solution also is valid for ordinary functions and also for just operators. So somehow, at least for ordinary functions, I should be able to convert this to an exponent. Somehow. Well, if this was kind of an exponent, the first term is fine. That's already in the expansion of the exponent. The second term is fine. That is the next term. Well, if this was just an exponent, this would have been the square of the integral multiplied by minus I squared divided by 2 factorial. Can I convert it to that? That will be the question. Let me look at a different expression. Let me look at this one. Remember, note that here, if I want to write this as the square of one integral, both limits had to be from t0 to t, not from t0 to the second integral should also be from t0 to t1. What am I missing? Well, I'm missing this term. I'm missing this term, this integral. Let me write it this form. If they were ordinary function, just writing vi of t1 first or the second wouldn't make any difference. If they were ordinary functions. They are not ordinary functions yet. If I could add this to the third term in my expansion, I could have written it as the integral squared over 2 factorial. That would have been great. Now let me do a trick. This integral, let me change the order of integration. So that I integrate over t2 first, and then over t1 first, then over t2. Well, t2 can take any value from t0 up to t. Remember, t1 can be down to t0, so t2 can take the value t0. But t1 is always less than t2 in first integral. So t1 is less than t2, so it should go at most up to t2, starting from t0. Sorry, this is... Yeah.
So at first T2 is before T1, right?
Yeah.
But then I change.
No, here, you see, in this integral, T2 is larger than T1. Lower limit of T2 integral is T1.
Because it has to be like that. Otherwise, all the time goes right to left.
I will come to that in a moment. Let me just finish. Now, I just want to rename these T2 to T1 and T1 to T2. You see, this integral over here is the same as this integral over here. Those integrals are the same. In fact, the only difference is here, yeah, they're identical. You see, this whole integral is actually equal to this integral over here in everything. So I can add this term from T0 to dt1, from T0 to T1 dt2, Vi of T1, Vi of T2 is equal to 1 over 2 from T0 to T1 dt1, from T0 to T1 dt2, Vi of T1, Vi of T2, plus from T0 to T1, T1 to T, because both integrals are the same. In fact, if these were ordinary functions, the integrand of the first integral and the integrand of the second function will be exactly the same. So I can just sum them up, and that will just give me the square of an integral. Now, what did I do in this change of variables? Just imagine this T1, T2 plane. T1 takes values from T0 up to T, and T2 takes values from T1. Well, T2 is equal to T1 is this line. This is T2 is equal to T1 line. So as T1 goes from T0 to T, here, T2 goes from T1 to T. T is here. So this is my integration domain. I'm integrating over this triangular region. Now, when I change my integration variables, what I'm actually doing is I'm integrating over the same area, but I will integrate T, no, sorry, yeah, here. When I change the order of T1 and T2 integral, I will integrate over T2 from T0 up to T, but for a given value of T0, T1 can take values from T0, from this value up to T1, up to T2. So rather than, my integration is kind of scanning that area. Instead of scanning vertically, I'm scanning horizontally. That's the only thing I did in my change of the order of integration. Now let's come back over here. Let me write this in a slightly different form. This is 1 over 2 from T0 to T1, dt1, from T0 to T. No, this is T, sorry. dt2. But inside I will have Vi of T1, Vi of T2 if T1 is larger than T2, plus Vi of T2, Vi of T1 if T2 is larger than T1. Is it? What I if you look at the region T1 in the T1, T2 plane, this is T0, this is T, T0, T. if you look at the first integral, is when t1 is larger than t2. So it is this area in the first integral. In the second integral, I have t2 is larger than t1, so it is this area. So if I combine both of these integrals, I am integrating over that square. But the integrand is different. If I'm in the horizontally scanned triangle, then vi of t2 is first on the right, vi of t1 is on the left. On the upper triangle, it's the other way around. So these step functions make sure that you pick the correct term in different triangles, making this square. Now, this whole thing is defined as the time-ordered product. This is defined as vi of t. Whichever time is first, it acts on the left. It is placed on the right. This is just a definition. And remember, in the first term, t2 is first, so vi of t2 is on the right. T1 is later, so vi of t1 is on the left. In the second term, t1 is first, so vi of t1 is on the right, and vi of t2 is on the left. What does that tell me? Well, I had this integral. But this is nothing but 1 over 2 factorial dt vi of t dt prime vi of t prime from t0 up to t squared. You see here. Now t1 and t2 integrations are independent of each other. I'm integrating, now let me write two steps. This is equal to 1 over 2 from t0 to t dt1, t0 to t dt2, time order product of vi of t1. This is what we had actually shown. Now, time ordered product, well, this is the definition when you have the product of operators at different times. When you try to sum them up, we also define it to be linear, which basically tells me that the sum, the time-ordered product of a sum is the sum of time-ordered products, which tells me that I can take it out of that integral. Integral is just summation. But now this is remember vi of t1 is now independent of t2, so I can take it out of the t1 integral. But now this integral is also independent of t1, so basically I have the product of two integrals. Squared. Well, let's go back. What we were trying to calculate was this one. This expression. what I had shown is this is equal to 1 plus time-ordered product of minus I t0 up to t dt1 vi of t1. Well, there's nothing to order there, so it doesn't do anything. Plus time-ordered 1 over 2 factorial time-ordered product of minus I t0 to t dt1 vi of t1 squared. You can repeat the same thing for the other terms. Cubed. Well, now I can sum them up. This is equal to the so-called time-ordered exponential of minus I from the integral from t0 up to t dt1 vi of t1. Well, we didn't really do much, to be honest. What we had is we had this infinite sum over here. We wrote it as an exponent, a time-ordered exponent. But the exponent of an operator, you interpret it as a Taylor series expansion, so if you want to make use of this exponent, you have to expand it anyway. Well, at least the time ordering expression shortens the expression. Let's say all of this term is just the cube of an integral now, as long as you put the time ordering there. That has been our achievement. So that is, well, our time today is up. Anyone last question? I do advise you strongly to go over this derivation on your own once, at least. Now, on Thursday, we will just pick it up from here and relate to this our scattering amplitudes. Remember, our purpose was not to solve for the interaction picture states, etc. Our purpose is to evaluate this expression.
Can I ask a question? You say that there is an interaction between the two particles at the time equals 0. You know that. How am I supposed to know that while looking at that?
We will come in the next day. We will. I mean, what I know is I'm creating my particles at some early time. I'm choosing my t equal to 0 to be the time around which my particles are interacting. That is how I choose my t equal to 0. They're interacting at some time. And hopefully when they are close by.
Actually, when I write this, bracket, I only see that there are some initial two particle states in the first. Then I use a time evolution. Then
That's the only thing I have at the moment. That's the only thing. I don't know whether the particles are even interacting or not. I don't yet have that. We will come to that in the next hour. It's not here.